Yes. And Matthew will talk about Bayesian spatio-temporal modeling for infectious disease outbreak detection. Thank you.
Thanks, yeah, thanks for the introduction. After you from STARS development. I'll be talking to you about one of the things I've been doing for my PhD. So this is joint work with my supervisors, Xavier and Simon Spencer. So it's on Bayesian spatio-temporal modeling for infectious disease outbreak detection. So what are some of the motivations for why we do this kind of research? So first one would be public health surveillance, right? Say especially in low and middle income countries where there is limited resources. So like we want to know where to like allocate interventions in cases like this. So it's more like trying to survey where there are outbreaks occurring at a specific moment. Another importance of what we are doing is that this is a model-based approach. There are other approaches to outbreak detections, but not fully model-based. So this is like a model-based approach to like quantify probabilities of when an outbreak is occurring, and then we have the opportunity to like forecast future outbreaks where possible. So suppose we observe infectious disease data from like spatio-temporal datasets from say our spatial locations across time. So what we are doing is we are decomposing the risks. So like we say conditional on the risks, which is the lambda t. Right, let me just stay here. So conditional on these risks, right? We assume that the count of the infection follows a Poisson distribution. That's this mean, where EIT is the number of susceptibles in the population. So we decompose the risks into this purely temporal component. This seasonal component, it's a cyclical seasonal component and a purely spatial component. Then we have this spatio-temporal component, which represents the outbreak. Right. So we have the temporal trend components, the temporal seasonal components, the spatial components, and this, right? So XIT is assumed to be an unobserved time homogeneous Markov chain. And literally what that means is that the transition probability matrix is assumed to be constant through time as the chain progresses. So one thing I would like to point out is that this method is based on a precise distinction between what is an outbreak, right? Because sometimes it's difficult to define what an outbreak is. So we assume, I'll probably have to write this down so that I can make reference to it. So, so you could think of this as eight sporadic cases. Then this be contribution of outbreak. Right. So it's important to say that you could still have spikes in here, but it's not necessarily an outbreak, right? Because what you have is just contributions from maybe temporal factors, seasonal factors, maybe during the winter, it turns out that you have more cases, right? Less during the summer, and then spatial factor, which is like how the space contributes towards it. So when there's an outbreak, right? So you would see that the Markov chain has just two states, which is like no outbreak and outbreak. Like when there is no outbreak, you see that there is no contribution from all of this. It's just sporadic cases at that point. So you have ZIT, which is like a transformation of the data sets at the previous time points. I'll give some specifications of what these are afterwards. Why this is more, you could picture this as like a regression coefficient of the increase on the risks of disease when there is an outbreak. That's what the model is. You could see that in this model, each of these components are random effects that needs to be modeled separately. So it's not just that you have components on each of them. So what are the prior models for some of this? So for the trend components, which is RT from the previous slides, like we assume that to be a second order random walk, which literally is that RT equals to R minus 1. See, right? And then we have these that follows this portion. Zero. And it's like a precision parameter for this is called a random walk. So this parameter governs how smooth the trend component is because it's a background trend. So you want a very smooth model for that. This is the seasonal component. It's a first order random walk, but it's cyclical. And that's why you see this T mod C right there. So it's, you could picture this as it's a sinusoid, right? That goes something like this. But like over all the domain of the time, it repeats itself exactly, but like as the same. So this is like a more parsimonious modeling instead of like allowing the seasonal component to like change shapes or so you just have for the seasons you require, and then it repeats over the time domain itself. So lastly, for the spatial component, the prior model is this. It's still a Gaussian Markov random fit, but it's what is known as the ICAR, the intrinsic conditional autoregression. So this is saying that the conditional distribution of this spatial component given its neighbors follows this Gaussian distribution, which is literally the average of its neighboring spatial components and the invariance right here. Okay, so these are some of the priors for the other parameters. So we have this gamma, which is like which rules the Markov chain. We have this almost vague prior for the precision parameters for each of this. So one thing to point out would be that these densities are all degenerates in the sense that they are not proper distributions. And why that is related to the previous talk where you have the precision matrix not being invertible. So in that case, you don't actually have a covariance matrix here, but you have a precision matrix, which is literally kappa R times RR, right? So RR, if you are familiar with graph theory, is what they call the Laplacian matrix in graph theory. So that's what kappa R is. And by solving that, you could derive what the components of that matrix is. And then you're able to like evaluate the density. Okay, so in picture, this is what the model looks like. You have the alpha parameters, which are the precision parameters of them, right? Influencing these latent components. So you have the transition parameters, which is governing the outbreak, and then you have this into this. So this is like the risks we are trying to and then that it also influences the observed counts we see. So yeah, back to some of the specifications of what the increase when the XIT is on. So these are some of the specifications for it. And you could see that for model 0, it's literally just sporadic cases. You don't have any spikes or increase in outbreak. For 1, you could see that it's a transformation of the cases in the current spatial location, right? So if you have at least one case in your spatial location, then you have one. This is just an indicator function. And for model 2, you could see that if you have for at least in your space or in your neighboring regions, and so on and so forth. And the model 7, which is just saying that irrespective of what the previous case is, either it's 0 or not, you always have an increase in risks if the Markov chain is at the first state. That's state 1, rather. So what is quite important to note right there is that this, like in some of the other models, this does not really control when there's an increase in this, because this can usually be 0 from some of the specifications right there. And if this is 1, so this switches it up, and then you go back to this, which usually means that the essence of specifying this Markov chain within the model is nullified, right? So we'll see the effect of that when we get to some of the results. So yeah, like from the title, this is a fully Bayesian framework. So we are trying to like target the posterior distribution of all of the model parameters. And literally, we set theta to be equal to all of the parameters, right? And then we define a subset of it, which is literally saying that we pick one spatial location, UI. And why we are doing this is because we want to make the assumption that conditional on a spatial location, the data sets are independent. So that's the assumption we are trying to make while we do this. And that's why we are able to bring in this product right here, right? So we have this posterior right here. But something is missing. XIT should be in here if we are doing data augmentation, because that's not observed in real life, right? So, and we can't do inference without knowing what that is. So one of the first things that we would want to do as statistician would be to sample the path of that, because it's literally a Markov chain, right? So we sample the path of that, and then we have a closed form expression for our likelihood. But that's very expensive to do, and because it's discrete, right? You don't have a continuous log posterior anymore. It's not like you have this discontinuity in your log posterior if you would want a continuous log posterior or something like that. So how not to decompose this, assuming that you want to exploit the fact that a probabilistic fact that you know that the sum of both should, like the probability of the entire sample space should be 1, right? So you know that if you sum each of those probabilities should give you the full thing you want. So this is more like trying to marginalize out what XIT is in a statistical sense, right? But you don't want to do it this way in brute force, because this sum right here for just one spatial location contains 2 to the power of t items, right? Your time points, because 2 is the cardinality of your state space for the Markov chain. So, and as that increases, you can imagine that this also increases. Okay, so how do we handle that? This is known as a forward filtering. We define this forward vectors that we are able to like roll over computations from the previous time points. And that usually reduces the time of the computational time for us. So what is this? This is usually the probability of your data sets in your spatial location from the first time point to a current time point. That's jointly with the Markov chain at that time point, giving all of your parameters. And if we are able to like run this forward in time up till the final time point, you can see that what we will have is literally substituting little t, it's capital T in there. And then you have the joint probability of all of the data sets and the outbreak at the final time point, right? And when you have that, you could literally just marginalize over the outbreak at the final time points. And then you have your marginal likelihood, which is literally what you need for your inference, right? So this is your marginal likelihood. Because what this gives you is the joint probability of all your data sets, right? with the outbreak at the final time point, and then you integrate that out, you are left with your likelihood, which is literally what you need for your inference. And then this is posterior outbreak probability. So I've written post hoc right there because since we are treating it as a nuisance parameter in inference, we really don't need it for now, right? We just forget about it and maybe compute it after inference. So that's why I've written post hoc right here. So I won't spend much time on some of this due to time, but literally what's going on is that if you look at the previous definition of the joint probability I mentioned, that's literally the first line right there. So if you are considering the first time points, you can see that it's just the joint probability of your data sets at the first time points and the outbreak at the first time point, right? And by your chain rule, so this is probability chain rule notes in maths. By chain rule, you could decompose that into this conditional probabilities, and then that's literally like the initial density of your Markov chain at the first time point, right? We have assumed that to be stationary distribution, and that's why we replace it as delta right there. So with that being said, if you break the very first definition right here, you can write that joint distribution as this. So the xit minus 1 is usually not of any importance, right, in this joint distribution, because if you picture the Markov model, you could see that xt minus 1 has nothing to do with the other thing. So maybe I'll just draw a picture. So you have x2, x3, xt. So in this case, this is like, you see that conditional on this is not relevant to this, right? You've broken the dependence between these two. So that's why you can literally bring in that xt minus 1 into this bit right there. So it's literally the same as the first equation. The third equation and the first one is the same thing, but you bring in x minus 1, right? And you say this sum right there is literally just marginalizing out down. So it's like bring down the integrate that again, right? Makes no difference. So literally that's what's going on. And you can see that you could break this into this, where all these are not relevant to it because they are conditional independence due to the structure of the Markov model. And then you have this. This is literally this by the definition of this. And then you have this being the emission probability, this being the transition probability of the Markov chain. And then you arrive here. So we did some MCMC to like draw samples. So we have like different MCMC sampling methods to like draw sample from the posterior. And one is the hybrid MCMC where we utilize the Gibbs updates. So like for some of the hyperprior choices, we have a closed form conditional for the posterior. So we literally just sample that using Gibbs. And then adaptive random walk, especially for the temporal components. Together with conditional prior proposal, which I might have to skip due to time, so I won't be able to like go into that. And also because we have a differentiable log posterior, we're able to like use the Hamiltonian multicolour, which requires a continuous density. And then you have the opportunity for even more sophisticated MCMC, like for those who are interested in diffusion. So I won't really go into the details of this due to time, but this is the conditional prior proposal for updating the temporal trend component. So this is also the outbreak probability 4, which is post hoc, right? And that's literally what helps us to like quantify where an outbreak occurs at the end. So I'll have to skip that, I'm afraid. So for model comparison, ideally, if you have the xit within, which is a discrete parameter, then you can't use dit even if it's a Bayesian model, because you have this discrete parameter, and then the DIC relies on the assumption of Gaussianity of all of your model parameters. So like if you are computing the deviance to compute the DIC, you literally you have this bimodal distribution for the XIT, which is 0 and 1, right? If you are sampling those. So like what would you take as a posterior mean of those two? So that's one of the reasons why you can't do DIC for that. So a standard Bayesian approach would be to like compute the model evidence, which is this I-dimensional integral right here. And we are using the importance sampling method. If you look at this integral right here, you'd see that the variance of this estimator, you see that the proposal density appears at the denominator, which means that if you sample at the extremes of the distribution, so you have a Gaussian, right? So if you sample here, like you have a very negligible density because it's light scale compared to like a T distribution, which is more heavy field. So it doesn't really solve all of the problem, but like it does solve the problem because the estimate is more stable if you use a T proposal, because obviously it reduces the variance for you. And then bridge sampling, which I won't really talk about. So some of the results, we have this 9 spatial locations, right? We assume that locations that are diagonal are not neighbors because they don't like touch each other. So the ones that touch each other are considered to be neighbors. And then you can say, so like this is used to for you. So these in red are like big cities. You can see them in red right there. The blue ones are literally like the small cities. So we simulated data sets on this space, right? And we know what the true outbreaks are because obviously it's simulation. We know what the true outbreaks are, and then we discard those. We discard them and like use the data sets that we simulated to do inference in the hope to like recover the true outbreaks, which are the values in pink, right? So you could see that the final model, which is like model 0, like really captures where there is an outbreak, although it's not complex. But compared to like other models, which where you have all these kind of uncertainties right there. This is a posterior probability of outbreak quantification. So the device is still more certain. It is so this is like an ROC to like quantify the accuracy, right? Because we know what the true values are and what the detected value are. So this is a simulation study trying to like validate if the model comparison method works well. And you could see we simulated from model 0 and tried to like run the inference on all the other models and see if you can recover the true model where the actual data sets came from. And that's why you could see this diagonal right here. We're able to like recover that. So this is an application to meningitis across 28 European countries, which you could see by the left right here. This is a map of the posterior relative median risks, which is actually the exponential of this guy, this UI, because that's the social contribution to that. Since like we have the analytical expressions of each of those components, and we have like the posterior predictive distribution, we are able to like make forecasts into the future of like when there's an outbreak. And of course, because this is a Markov chain, you could see that after a few months, converges to stationary distribution, nothing more interesting is going on. So this is more like for a very short-term forecast, else you just get to stationary distribution and nothing else goes on. Yeah, and summary, we have an R package that implements all of this, both the MCMC and the HMC. If you have access to GPU, the HMC is accelerated. If you have CPU, it's C++ accelerated. And yeah, you can find the paper on archive. And yeah, I think that's all. Thank you.